Yeah, well, welcome everyone here and on Zoom. Today we'll have the comprehensive exam for Johnny Dorigo Jones. So the way, as per our tradition, these usually go, it'll first be a presentation for everyone. Johnny will do a presentation for what, roughly 40 to 45 minutes, something like that.
Yeah, 40.
And then we'll have questions from the general audience. Before then, there's a closed session with the committee. Yes, well, remember, Johnny will tell us about his work, which I understand is recently accepted for publication on validating posteriors obtained by emulating or jointly fitting mock data of the global 21 centimeter signal and Hezi galaxy UV.
That's exactly how you should say it. Yeah.
Take it away, Johnny.
Thank you. Thank you. So hello everyone. Thanks for coming early to my comps talk today. I'm going to be talking about my research done over the last year and a half with my advisors, Jack Burns and David Rapetti. And yeah, the work is titled Validating Posteriors Obtained by an Emulator when Jointly Fitting Mock Data of the Global 21 centimeter Signal and Hezi Galaxy UVLF. So just to start out with, we're going to go over what each of these terms mean before looking at the results. So yeah, let's do that. So we're going to start out with the global 21 centimeter signal, just describing what that is, some background, because that's really what we're interested in here. So brief overview on cosmology. The universe started with a Big Bang about 13.8 billion years ago. And the universe was very dense and very hot, so neutral hydrogen hadn't formed yet. And then once the universe expanded and cooled somewhat more, recombination occurred and electrons and protons were able to recombine and form neutral hydrogen. And so this is sort of like the baby picture of the universe where photons were able to stream freely for the first time. And that's the cosmic microwave background, which is considered the highest redshift that we could possibly observe to, because that's where photons were able to stream freely for the first time. And then following that period was the dark ages, where there was no astrophysical objects had formed yet. So there were no stars or galaxies. And so that period is dominated by cosmology. And so that's one of the really unique areas that the 21 centimeter signal is able to probe rather than other observations. And so then we go on to the cosmic dawn, which is when the first stars and galaxies began to form around redshift of 30 or so. And we're going to talk really quickly about what redshift means soon. And then the cosmic dawn occurs and all the radiation from those first stars and galaxies begins to ionize the intergalactic medium, which is the space between galaxies, and hydrogen turns from neutral to ionized. And so this is a picture of the universe that you should have in mind when we're talking about the astrophysics that can be gained from studying the cosmic 21 centimeter signal, where the backdrop is the cosmic microwave background, and there's neutral hydrogen all throughout the universe that can emit this signal. So we're really interested in the astrophysics and the cosmology related with each of these periods that we can probe. So now let's talk about what the 21 centimeter signal is. So it's a spectral transition in neutral hydrogen. So we have an electron and proton in a neutral hydrogen atom, and they have a quantum mechanical property called spin. And so these spins can either be aligned or anti-aligned. And when the electron flips its spin with respect to the proton, a photon is released. So it's called a spin flip transition. And this is a hyperfine level that comes about because of this interaction of the spins. And so this is in the ground state of hydrogen again. And so a low frequency photon is released at a rest wavelength of 21 centimeters. And so that's what the 21 centimeter transition is. So this occurs in all neutral hydrogen that exists throughout the universe. And there's enough neutral hydrogen where the signal could be observed. So due to the expansion of the universe, the universe is expanding. And so redshifting occurs, which just means that the wavelength of light increases as it reaches us. So it reaches us at present day, which is redshift 0. And so due to that expansion, we observe this 21 centimeter signal at somewhat lower frequencies of 10 to 200 megahertz, corresponding to redshifts greater than 6 or so. And so there's a spin temperature associated with this 21 centimeter transition. And all that means is from the Boltzmann equation, which is basically understanding that how many electrons we have, or how many hydrogen atoms we have in one state versus the other. So the higher energy state or the lower energy state. And so basically the spin temperature quantifies the relative number densities of those two states. So that's really the quantity that we're interested in when we're talking about the 21 centimeter transition is the spin temperature. And here at the bottom, I showed the equation for converting between observed frequency and redshift. So this is the scale factor of the universe. And so frequency decreases with increasing redshift. So how do we actually observe the 21 centimeter signal? So as I talked about earlier, the cosmic microwave background is the highest redshift that we could observe to. So that's considered our background, our radiation background. And all between us and the cosmic microwave background are clouds of hydrogen in the intergalactic medium. And so all the neutral hydrogen atoms in those clouds are undergoing spin flip transitions. And so they're emitting these 21 centimeter photons. And so basically, so there's a spin temperature associated with that, and there's a temperature associated with the cosmic microwave background. And the 21 centimeter signal induces this temperature difference as seen at the backdrop of the CMB. So it induces a difference in brightness temperature, which is what we observe here on Earth. And so in the top right, I show the equation for radiative transfer. And so the observed brightness temperature that we see is a function of the spin temperature of hydrogen, which quantifies those relative number densities in those states, and the temperature of the background, which is assumed to be the cosmic microwave background. And so what we'll talk about soon is that the spin temperature is closely related with the gas kinetic temperature. And so basically to understand how the spin temperature changes, we really have to understand how it couples with the gas kinetic temperature. And so one of the things that you should get from this slide, the main thing is that the spin temperature needs to be different from the background temperature for us to observe a 21 centimeter signal. So this global 21, so the global means sky average. So we average the signal over the entire sky. And so this signal has not been measured yet. And there's a lot of difficulties faced with measuring it. So these are some of the reasons why it has not been constrained yet. And so what we're looking at mostly is models that what we would expect it to look like until we actually obtain a measurement. And so some of the difficulties faced in measuring this global 21 centimeter signal is an intense foreground produced by the Milky Way. So we live in the Milky Way, and there's electrons, relativistic electrons all throughout. And so they emit synchrotron radiation, which follows a power law energy distribution. And so that's about 4 or 5 orders of magnitude larger than the underlying signal that we want to measure. And so that's one of the main systematics that needs to be understood. And so some of the other ones that make it difficult to measure is we need to understand the radio beam pattern. So that's an example of the radio beam pattern on the sky and its chromaticity, how it varies with frequency. And so there's also severe distortion by the ionosphere for measurements that are made on the surface of Earth. So the ionosphere, there's a lot of turbulence that disrupts the wave pattern. And so that makes it very difficult to understand the signal that we receive if we're measuring it from the surface of Earth. And so especially for the dark ages, because that's the lowest frequencies, those cannot be observed on Earth. And so we need to go to space outside of the ionosphere to observe the dark ages, perhaps on the moon, on the surface of the moon. And so one of the last systematics is radio frequency interference, so just noise. Any types of radio noise that could disrupt, that don't come from the 21 centimeter signal. And so these are all different systematics that need to be understood and accounted for in the field in general going forward. But before we do that, we need to understand the astrophysical parameter constraints that we can get from the global 21 centimeter signal. And so that's what my work focuses on. So the global 21 centimeter signal, in the top right, I show the canonical model for it. So we can see that the brightness temperature of the 21 centimeter signal basically just depends on these 2 or 3 quantities. So this is as a function of redshift, of course. So let me just explain this plot that we see in the bottom really quickly. So this is an example of the global 21 centimeter signal produced by the model. So this is not actually measured yet, but this is what we might expect it to look like based on physics and cosmology. And so these are all the periods that I discussed earlier. So in the y-axis, we see brightness temperature, which is what we discussed. It's the intensity of what we're observing. And in the x-axis is as a function of frequency or redshift. So on the left side is the earliest times in the universe at the highest redshifts. And so that's the dark ages. And then we go to lower redshifts where the cosmic dawn and then reionization occurs, which I touched on earlier. So that's the picture that you should have in mind when looking at the global signal here in the bottom. But just going back to the model, so basically it depends on those two quantities that we've talked about, the amount of neutral hydrogen in the universe and the spin temperature associated with the 21 centimeter transition. And so specifically the ratio of the background temperature and the spin temperature. So in the numerator is the background temperature, which is assumed to be the CMB, and then the spin temperature in the denominator. So we need neutral hydrogen to observe this signal. So once reionization occurs and we have no more neutral hydrogen in the universe, we can't see a signal anymore. So we need XH1 to be greater than 0 to observe the signal because of the 21 centimeter photons being emitted. And we also need the spin temperature to be different from the background temperature, which is what I talked about. So we can see that if the spin temperature is less than the background temperature, then the signal is seen in absorption. So the brightness temperature is less than 0. And so these two troughs come about because of that, because the spin temperature is less than the radiation temperature at those two points. So let's talk about what that means. So how these two absorption troughs come about physically. So why is the spin temperature less than the radiation temperature in those two troughs? And so one other thing I just want to note is that, so these two quantities, the neutral hydrogen fraction and the spin temperature, those are computed by our model over some given redshift period that we're interested in. And so those are the quantities that our model really needs to be able to accurately calculate in order to model the brightness temperature. So let's talk about those two troughs. So there's a coupling mechanism that occurs between the spin temperature and the kinetic temperature. And this is what allows the spin temperature to be driven below the background temperature. So in the dark ages, because it's very dense, we have a bunch of these neutral hydrogen atoms. There's a collisional coupling that occurs between these neutral hydrogen atoms. And because those are within an adiabatically expanding gas, so the universe is expanding at that time, so the gas is expanding cooler than the CMB is cooling. And so essentially the gas is cooler than the background because of that adiabatic expansion. And so the spin temperature is less than the background in the dark ages for that coupling reason. And then the dark ages continues to go on, the universe expands, and so collisional coupling becomes insignificant. And so the spin temperature relaxes back to the background temperature. And at that point around redshift 30, you can see it says first galaxies form or first stars or population 3 stars. And so at that point, they release a lot of intense UV radiation into the environment in the form of Lyman series photons, Lyman alpha. And so those Lyman alpha photons scatter off of neutral hydrogen atoms, and that causes a spin transition to occur. And so that's another coupling mechanism that occurs between the spin temperature and the gas kinetic temperature at the start of the cosmic dawn, due to the UV radiation released by the first stars and galaxies. And so due to that coupling, the spin temperature is coupled again to the gas, and the gas is again cooling. It's cooler than the background because it's adiabatically expanding still. And so there's another absorption trough that occurs. And then at the bottom of that trough is when X-rays produced by these first stars and galaxies become important, and that begins to heat the intergalactic medium and raise that spin temperature because it's still coupled with the gas back to the background temperature. And so the brightness temperature again goes near 0 because that ratio of the spin temperature and radiation temperature is 1. And so we don't know if it goes into emission or not. That just depends on the amount of X-rays that are released by those first objects. And so yeah, that's an understanding of how these two troughs form. And we're not sure if it reaches emission or if it's not an emission at reionization. That'll be constrained by observations and by measuring this actual signal. So those are the 3 periods and the coupling mechanisms that occur and the physics that's going on behind the global 21 centimeter signal at each of these redshifts.
How about reionization in the concept?
Yeah. So reionization is when the X-rays and UV radiation released by the first stars and galaxies heats all of the gas, all the hydrogen in the intergalactic medium, and then there's no more neutral hydrogen left, and so the signal goes back down to zero because we need neutral hydrogen to observe the signal. So now that we've talked about the global 21 centimeter signal and the background behind that, let's briefly move on to the high redshift galaxy UV luminosity function and why we're interested in that in this work. And so briefly, the global 21 centimeter signal is a way of constraining the astrophysics and cosmology with a very large redshift range, so going into the early universe. And the UVLF is basically another probe that we can use for lower redshifts in the epoch of reionization and potentially into the cosmic dawn that can give similar constraining power that we can use to improve our constraints. So let's talk really quickly about what the UVLF is. So here I show an example of what the UV luminosity function is. So Hubble Space Telescope and JWST have performed many extragalactic surveys, basically observing the farthest galaxies in the universe. So very, very faint galaxies at redshifts of about 7 for Hubble, and James Webb is expanding this to redshifts of 15. And so from these galaxy observations, you're able to construct a luminosity function, which is the number density of galaxies per UV magnitude. And you can measure that at multiple redshifts from us. So here in this paper from Bones et al., which is the UVLFs measured by Hubble, it's showing the UVLFs at these different redshifts, 4, 5, 6, 7, and 8. And so the main point here, these observations are done in the near infrared, but it's probing the rest ultraviolet of these galaxies because it's at a higher redshift. And so because it's probing the rest ultraviolet, the shape of this UVLF primarily depends on the formation of these young massive stars. And that's because they dominate the light from star-forming galaxies at these redshifts. And so they release a lot of intense UV radiation. And so the shape of the UVLF primarily depends on the formation of those stars. And so the UVLF is a direct probe of the star formation efficiency parameters. Whenever you see SFE in this presentation, that's what that means. So the star formation efficiency of those stars. And so the UVLF can be fit along with a measured global 21 centimeter signal to improve constraints, specifically on star formation parameters. So now that we've gone over the background of what the global signal means and what the UVLF is, let's talk about some of the methods. So what do we mean by jointly fitting mock data? So Bayesian inference is what scientists use to obtain parameter constraints given some observed data. So when we have data in hand, what kind of constraints can we get on our parameters in a given model? And so that's what Bayesian inference is used to do. So we have a model to describe our data, and we want to constrain the parameters in that model with some data that we have. And so here I'm showing Bayes' theorem, which is a way of estimating the posterior distribution, which is on the left. That's the posterior distribution on the left, and on the right-hand side is the likelihood function. That's the L multiplied by our prior knowledge and divided by the evidence. So that's a lot of words there. But basically the main thing that we're interested in here is the likelihood function, which is it's constructed with our data and our model. And so it's essentially the probability of our data given this parameter space in our model. And so what we want to do is search that likelihood function, is explore the values of that likelihood function over the parameter space that we're interested in, and to converge on the best parameter estimate. So we want to maximize that likelihood function through this Bayesian inference technique. And just again, the likelihood is a function of our data and our model. And what we'll go on to talk about later is that we use either the full model for the global signal in that likelihood or an emulator as the model in that likelihood. And so this is just an example in the bottom right showing some example parameter space and how the likelihood contour continually decreases as we remove these live points, they're called. So you generate some number of live points in your parameter space. So let's say 1 would be our first live point, and then you continually replace it with live points of higher likelihood. So that's how nested sampling works, and that's the method that we use to perform Bayesian inference. And you might have heard of MCMC. That's another common way of doing this, but nested sampling is basically supposed to be better for multimodal distributions and high dimensional parameter spaces. And so, yeah, this is how nested sampling works. You generate some live points, and then the likelihood contour eventually converges on the best parameter estimates. And so this is the technique behind what we're doing, or the theory. So we plug our data and model into this likelihood and search it over this parameter space. So how do we model the global 21 centimeter signal? So we use a semi-analytical, physically motivated code called Aries, which was developed by another grad student at CU in the last decade. And so we use Aries to simulate both the global signal and the UVLF, so it's able to model both of those. And so Aries is the union of a 1D radiative transfer code and a uniform radiation background code. And so those are the two physics components that we need to model the 21 centimeter signal, is performing radiative transfer and evolving that radiation background in order to model the brightness temperature. So the input into Aries is the emissivity, so all of the radiation that's produced by galaxies, the galaxy population, and that's derived from the dark matter halo mass function. And then the output from Aries is the ionization and thermal properties of the bulk IgM, which is what's needed to model that brightness temperature. And so the main quantities that we're interested in are the neutral hydrogen fraction and the gas kinetic temperature, which is closely related to the spin temperature, as we talked about. So here on the right, I just have an example plot showing how many orders of magnitude the temperature might vary, and you see the dashed line is the kinetic temperature, solid line is the spin temperature, so those are very close. But yeah, so these vary quite a bit over this redshift range being looked at in this paper. This is not from Aries, this is from a different model, but it's a similar conceptually. And the solid line is the neutral hydrogen fraction, and we can see that as we get to low redshifts, the neutral hydrogen fraction begins to go down because the universe is becoming ionized and we don't have any neutral hydrogen left around redshift of 6 or so. And so, yeah, this is how our code works in terms of how we physically model the global 21 centimeter signal. And so that's Aries. So you might ask, why do we even need an emulator if we're able to model it? And so Aries, as we just talked about, is able to simulate the global signal in a matter of seconds, which might sound fast, but this becomes very computationally demanding and expensive when we're performing an analysis that requires on the order of 100,000 model evaluations. And that's what's happening when we search the likelihood function throughout this parameter space. Is we're evaluating the model 10,000, 100,000 times or even more. And so for a model that takes on the order of seconds to evaluate, that can become very computationally demanding. And so we need an emulator to speed up this process. And basically an emulator is just a neural network, which I'll talk about later. But an emulator does not perform all the physics that a simulation does. It's just able to, you pass it some parameter values and it estimates the signal very quickly, which we'll talk about. But an emulator is much faster than this. And so emulators are needed to efficiently search the parameter space. And emulators will be useful, especially in the future for upcoming real experiments that must constrain many free parameters caused by additional systematics. So that's one of the main reasons that emulators will be useful going forward, that and the speed. However, so there have been some emulators developed for the global 21 centimeter signal, but we have a very poor understanding of the accuracy of these emulators. So basically, people are able to perform this emulator on mock data, but before they haven't known how accurate those constraints are that they get. So those posterior distributions that we talked about. And so where my work fits in is that for the first time, we're able to compare the parameter constraints from an emulator for the global signal to those obtained when using the full model that the emulator is trained on. And so basically we're able to use an emulator and the full model and compare those constraints for the first time here. So what parameters are we constraining? So I've talked all about these parameters that we're estimating the posterior distributions of. And so these are physical parameters within the Aries model. So there's 8 of them. You can think of it as 8 dimensions that we're trying to constrain in the nested sampling analysis. So 4 of them control the efficiency of UV and X-ray photon production per unit star formation in galaxies. And so those are the top 4 shown in this table: normalization of the X-ray luminosity star formation rate relation, escape fraction of UV photons, minimum virial temperature of star forming halos, and hydrogen column density. And so these are all common parameters used in simulations that people would like to constrain, but none of these parameters have been accurately constrained from observations yet. And so that's why we're interested in measuring this global signal. So that's 4 of the parameters, and then the other 4 control the star formation efficiency, which we talked about briefly earlier. And so here at the bottom, I show the double power law model that is used in Aries to model the star formation efficiency. So it's a double power law in this dark matter halo mass. And so basically there's 4 parameters in that double power law, and those are the second 4 parameters that we're constraining. So we're constraining all these 8 parameters together in this nested sampling analysis. And so basically to do that, we need to pick values for all these parameters to generate the mock data that we're fitting. And so how do we pick values for these parameters to generate that mock data? So what I'll talk about on the next slide is that for the star formation efficiency parameters, we obtain fiducial values by calibrating to a real UV luminosity function. And for the other 4 parameters, those values are obtained just by picking typical values used in the literature or from simulations for those 4 parameters. So I've talked all about the mock data that we're fitting, but I haven't shown it. So here it is. So here on the left is an example of global 21 centimeter signal produced by Aries using those fiducial parameter values. So that's the blue curve here where we see the dark ages trough here at high redshifts, and then this is the cosmic dawn trough, and then reionization. And on the right is the UV luminosity function. So the red points are data from Hubble, from the Hubble Space Telescope, and the black line is the model from Aries. So in Meroka 2017, they calibrated the Aries UVLF model to these real measurements in order to obtain the star formation efficiency parameters that match those measurements. And so those are the values that we use to create our mock data. And so for all of our analyses, we fit these same 2 realizations of the global signal in UVLF. And here in the top right, I'm showing what the joint likelihood is. So essentially, we are searching 2 different likelihoods through this parameter space, and then we combine those log likelihoods to form a joint likelihood. So when I say joint fits, this is what I mean. We're fitting these 2 data sets together and exploring their likelihood throughout the parameter space. Oops. So we've gone through what the global signal means and what the UVLF is and what it means to jointly fit mock data sets by doing Bayesian inference and nested sampling. And so now let's go on to the emulator. We trained the publicly available neural network emulator called Global EMU. So there's just about 2 emulators currently that exist, 2 or 3 that exist for the global signal. This was the only one at the time. Or yeah, there may have been 2 at the time, but we choose Global EMU to emulate Aries. And so here in the top right, I show a schematic from the original Global EMU paper that shows the network architecture. So on the left is the input nodes. So those are the parameters that you're trying to constrain. So basically you pass some parameter values to your network, and a series of mathematical operations occur, so these nodes are trained by this training, which I'll discuss. And so you pass those parameter values to your network, and it spits out the estimate of the temperature, of the brightness temperature. And so basically the way that this works is you generate a large training set generated by the Aries model. So that's what all these black curves are in this left plot. So those 8 parameters that I talked about earlier, we vary those parameters over wide ranges, and that's how you create this training set. And so we trained Global Emu on a very large training set. We tested multiple different sizes, and we're using a training set size of 24,000 signals, which is quite large. So then we train Global Emu on that to have it learn all the features of the Aries signals. And then at the right is the test set, the so-called test set, which is generated separately from the training set. And the black dashed curves are generated by Aries, and the red curves are generated by the emulator. And so we see that Global Emu is quite accurate when we're looking at the signal realizations. And so the error of the emulator when we're looking at the realizations is on the order of 1 millikelvin. And so another thing is that we chose a network architecture of 3 hidden layers of 32 nodes. So we tested multiple different architectures to see what gives us the most accurate emulator. And so there were multiple steps going through this in order to optimize the accuracy of our emulator. So now that we've discussed emulating the global signal and modeling it, we can now go on to discuss some of the results. So what happens when we use this emulator in the likelihood to obtain parameter constraints, and what happens when we use Aries in a likelihood to obtain parameter constraints. And for the first time, we're able to compare those and evaluate the accuracy of emulators. So let's talk about those parameter constraints. So now this is a corner plot. So there's a lot of information here, but we're going to go through it. So on the diagonal are the 1D posterior distributions. So these are for the 8 parameters, again, that we're trying to constrain. And so they're the 1D posterior distributions, and then on the off diagonal are the 2D posterior distributions between each of the parameters. In red are the posteriors obtained by the emulator, and in black are the posteriors obtained by the model Aries. And this is for a noise level of about 25 millikelvin on the Mach global signal that we're fitting. So that's something I didn't really mention earlier, is that if I go back to this slide, so this blue signal, we add noise to that, and then we're seeing the parameter constraints that we get for different levels of noise on that blue signal. So this is it being shown with no noise. So yeah, so these are the posterior distributions for a noise of 25 millikelvin, or about an integration time of 100 hours for a 21 centimeter experiment. And so, and this is a standard time considered in the field for a noise on a signal, or a standard amount of integration time for a 21 centimeter experiment. And so basically what we're seeing is that the posterior distributions are very similar between the emulator and the model. However, there are some important differences, which is one of the main results of this paper. But we see, first of all, is that Aries is recovering the fiducial values. So that those are the blue lines, the blue vertical and horizontal lines are the fiducial parameter values that were used to generate the Mach data that we're fitting. And so we want to recover those fiducial parameter values in this analysis. And so we see that Aries is doing a pretty good job. Basically, it's recovering each of those parameters exactly. The peaks of the distributions or the mean are all very similar. And so another thing I should say is that these are zoomed in ranges compared to the full prior ranges for the parameters that we're exploring. So these posterior distributions are quite constrained on the fiducial values compared to the full range that we're exploring. And so Aries is quite accurate, and Global Emu represents it fairly well, but we see that for 2 parameters in particular. So T-min, which was the minimum virial temperature of star-forming halos, and gamma low, which is one of those star formation efficiency parameters. Global Emu is biased by about 3 or 4 sigma, which we'll talk about later. So this is one of the main results of the work is that for a standard integration time, we're able to obtain pretty strong constraints using Aries, and Global Emu also obtains relatively accurate constraints, but there are important differences that must be accounted for going forward. So now we're looking at a noise level for a slightly higher, so now we're looking at the posteriors for when fitting a signal with a slightly higher noise level, so less integration time of a 21 centimeter experiment. And so this is also considered somewhat a standard to high noise level of a 21 centimeter signal. And so now we can see that for a slightly higher noise level, global EMU is even better able to represent the area's parameter space. And so these posterior distributions are basically exactly the same with some minor differences. And so areas and global EMU both obtain pretty accurate constraints at this 50 millikelvin noise. But we see that there is a bias for one parameter, T-min, so it's a little bit away from the fiducial value. And I'll talk about that more later, but the general idea here is that due to a higher noise level in the signal that's being fit, constraints are harder to get for parameters, just due to there being less constraining power from the data. And so that's how that bias could come about. But so the main idea, so flipping between these two plots again, we see Aries is pretty well accurate between the two noise levels, and global EMU becomes even more accurate when we go to higher noise levels with respect to Aries. And so what I'm going to talk about in the next slide is when we actually compare each of these red and black distributions. So now we're looking on a very fine level of how accurate is global EMU compared to Aries. So if we look at each of these red and black distributions, we're going to calculate the number of standard deviations between them. So that's done by calculating the mean of each red and black distribution. So, let's take this one, for example, the mean of the red one and the mean of the black one, and then we subtract those and divide by the standard deviation of the black distribution. And so this is to quantify how accurate global EMU is for each parameter. And we do this for the 5 different noise levels that we test. So I've just shown you the full posterior distributions for 2 standard noise levels considered in the field. And we also do this for more optimistic noise levels on the signal and for more pessimistic noise levels. So more or less integration time. So what I'm showing in this plot is the emulation bias, what we just discussed. For those different noise levels, so all the different colors are the 8 parameters that we're constraining. And so we can see that for increasing noise levels, the emulation bias decreases in general. And so global EMU is able to very accurately represent the Aries parameter space at these 50 and 250 millikelvin noise levels. But at somewhat lower noise levels, it's harder for global EMU to so accurately constrain these parameters, getting exactly the right values with respect to Aries. And so we see these biases for 2 parameters, what we just discussed for T-min and gamma low. So if I go back to the 25 millikelvin plot, you can see the red distribution is slightly higher, about 3 or 4 standard deviation higher than the black distribution. And so that's what's being shown here for the 10 and 25 millikelvin noise level. So yeah, the emulation bias is less than 1 for those higher noise levels. And then as we go to lower noise levels, the emulation posteriors become less accurate than the true Aries posteriors. But again, I should say at all of these noise levels, the Aries posteriors are relatively well constrained, except for some true biases at the smallest noise levels and at the highest noise levels, which we talked about, is due to the lack of constraining power at the high noise levels. So really quickly, let's talk about the Bayesian evidences. So I talked about the Bayes factor before. So the evidence is the denominator in that Bayes theorem, and it's called the marginal likelihood, but it's used to compare the results when using your 2 different models. And so what I'm showing here is the log Z, the log of the evidence for these different noise levels that we tested using either global EMU or Aries. And so these evidences are all very similar, and when comparing for each noise level respectively between global EMU and Aries, we find that the Bayes factors indicate statistically no preference for either Aries or global EMU in fitting the data. And so this is an interesting result, because we see that from the Bayesian evidence, they're basically saying that they're fitting the data very similarly. But when we go to the level of looking at the posterior distributions, we do see that there are some important differences that should be understood for why this emulator is causing these biases.
Very quickly, go back to that table.
Yeah.
Column, seconds per evaluation. What is that?
Yeah, so that's like I said, we perform many likelihood evaluations. So that this column is showing how many likelihood evaluations are being done for each analysis, and the seconds per evaluation is yeah, the amount of basically we take the entire time of the run and divide by the number of evaluations. So it's the time per model evaluation.
This thing is speed up, I multiply those two columns.
Yeah. So this is a yeah. So the speed is more apparent when we're only fitting the global signal. This is showing joint fits. And so for the UVLF, that's being modeled by Aries in both cases. So that's most of the time that you're seeing for why global EMU is at such a high seconds per evaluation here. It's about 0.01 seconds per evaluation when looking at only the global signal. So yeah, the Bayes factors indicate that these are very similar fits to the data using either the full model Aries or the emulator global EMU. But what we see when looking at the posterior distributions that there are important differences. So now I'm showing the 1D posteriors for these 8 parameters for 3 noise levels. So an optimistic noise level, standard, and a pessimistic noise level. So 10, 25, and 250. And basically what we're seeing here is that for the most pessimistic noise level, it's harder to constrain certain parameters. And so this is an idea called posterior consistency or Bayesian consistency. And the idea is that as you integrate for longer, you have more and more data. So you have more degrees of freedom in your data vector. And so your posterior distribution should converge on the fiducial value, the true value. And so we see as we go from 250 to 25, so from the gray to the purple to the yellow, the posterior distribution is becoming more and more peaked around that fiducial value indicated by the blue line. And it's also becoming more Gaussian or more peaked, which is because it's satisfying the central limit theorem as we are increasing the number of samples. And so one of the other things I want to point out here before going to the next slide is that, so these 4 parameters on the right are the star formation efficiency parameters, and on the left are the parameters, the other 4 parameters, the astrophysical parameters. And so the star formation efficiency parameters are relatively well constrained at all of these error levels, and that's because they get most of their constraining power from the UVLF. And so it doesn't really depend on the noise of the global signal so much. But we see that for these 4 parameters, they get a lot of constraining power from the global signal, and so they need a more accurate global signal in order to obtain good parameter constraints. And I should say that these distributions are obtained using Aries, but they're very similar if we were to look at the ones obtained using global EMU. So that's what I'll talk about on the next slide is the star formation efficiency parameters is what we're focusing on. So what I'm showing here, in the past, what we've looked at is joint fits, so the posteriors when searching both of those likelihood functions throughout the parameter space and combining those into a single likelihood. But now we're fitting each mock data set individually, so separately, and we're looking at the parameter constraints that we get from each individual data set. So what parameter constraints do we get when only fitting the UVLF, and what do we get when only fitting the global signal, rather than their combined constraining power? So what we see in the green distributions and is when only fitting the UV luminosity function, the star formation efficiency parameters are rather well constrained. As you can see, the green distributions are centered on the fiducial values, and these 4 parameters are relatively unconstrained, and that's because those parameters are not probed by the UVLF. It's mainly only the star formation efficiency parameters. And then when we look at the red and black distributions, we again see that global EMU does a pretty good job at emulating Aries when only fitting the global signal. But we see that these star formation efficiency parameters are rather unconstrained when only fitting the global signal. So from this, we see that we really need to combine the UVLF with the global signal in order to accurately constrain the star formation efficiency parameters in particular, and to obtain the constraints that we looked at here. So now we've talked about all the constraints that we get from these analyses. So I'll wrap up with conclusions. So we've been able to show strong parameter constraints can be achieved on this 8-dimensional parameter space in a Bayesian inference analysis when combining UVLF data with the global signal. And so in the future, combining JWST UVLF measurements with 21 centimeter measurements will be necessary to accurately constrain certain astrophysical parameters, in particular those SFE parameters, as we looked at. And emulating the global signal in general is very valuable in speeding up analyses, we found, and efficiently exploring these parameter spaces, and especially these multidimensional parameter spaces, which are very hard to constrain. And you do this by generating training sets and testing many different networks as we did. And so we find that global EMU obtains quite accurate parameter constraints compared to the full model areas, and this wasn't looked at before. However, global EMU is biased for 2 parameters at that standard noise level that we looked at. And so this emulator bias needs to be understood and accounted for going forward to ensure accurate parameter constraints in 21 centimeter experiments. So thank you.
Thanks, Johnny, for very clear, excellent talk. Question from the general audience, either in person or on Zoom.
Joshua.
Is there another way of comparing the posteriors to see how accurate they are for the emulator versus areas that's also sort of independent of like the training set versus test set RNSE?
Yeah. So we can look at the signal realizations from those posterior samples is one thing that we can do. And this isn't a plot that I talked about in the talk, but it's interesting to look at. So if I go to these, basically this is showing the posterior samples that you get. So those posterior distributions I showed, if you take those parameter values and pass those through the model, this is the signal realizations that you get. And so this is an interesting way of looking at the global EMU constraint compared to Aries. Rather than looking at those parameter constraints in particular, you're looking at how the actual constraint differs between global EMU and Aries at these different redshifts. And so this is an interesting thing that we're looking at now to try to understand why these biases are coming about with global EMU.
Other questions from the general audience? Are there any questions on Zoom?
Yeah, I think so.
So clear. Okay, if not, it's also Twitter. If not, no worries, then let's thank Johnny again. Okay, so now we can excuse the